If possible, solve the system of equations. Use any method. If there is not a unique solution to a system, say why. 9x equals negative 69 minus 7y. Negative 4x plus 4y equals negative 12. Okay, we're being given a system of two linear equations. They're both linear because the exponents on both variables are positive 1 in both equations. So I'm going to go ahead and issue equation numbers. The first equation I'm going to call equation 1, and I'm going to make that relate. I'm associating the color blue with that first equation. The second equation I'm going to label as equation 2, and I'm going to refer to that, kind of associate the color green with that initially. One of the issues that I'd like to point out is, when I'm looking at these answers, these actually are ordered pairs. Answers A, B, and D are ordered pairs. What's the meaning of that? Those are unique solutions to a system. Ordered pairs, these ordered pairs would translate to graph as points, like 3 individual and unique points on a coordinate system, a rectangular coordinate system. So the meaning behind that is a line represents the solutions, at least a partial example of where you would find solutions to an equation. So equation 1 here, if we were to graph equation 1, it may graph as this line, and that's where I'm going to kind of use colors. Equation 2, and I'm totally guessing, and I'm just presuming what how this line would graph. I don't even know if it goes up to the right, down to the right. I don't know. I'm just trying to make a graphical representation, like a schematic, of what these ordered pairs mean. The blue line here would represent partial set of solutions of ordered pairs, x's and y's, x, y, ordered pairs that would graph from using the equation with whatever method. Now, if we were to graph the equation 2, and if the line for equation 2 intercepted the line for equation 1, they may, all the points on this green line, however it actually falls in space, would show a sample of the solutions that are associated with this equation. But where the two lines intersect, that point of intersection would lie on both lines and form an ordered, or be represented by an ordered pair. Now, solutions to the one line and solutions to the other line, they're exclusive of each other unless they intersect, the two lines intersect. This one red ordered pair would represent a solution that is shared by both lines, a point that lies on both lines, coincident to both lines. And that, if we were to take the value of x and the value of y and substitute them into each of these two equations, what it means is we would get a true out of that point for both of these equations if we checked them. Okay, so we're looking for this represents the solution, if it exists, the solution to the system, to this system of two linear equations. Okay, so let's get to it. Initially, I'm going to rewrite the equations that we're being given, and we're being given 9x equals negative 69 minus 7y. Here's equation 1. I'm going to go ahead and put the equation numbers on the left. Give us a little working room. And then with the equation 2 that we're being given is negative 4x plus 4y equals negative 12. Now there are several methods to solving a linear system. There's substitution method and there's elimination method for 2 examples. Graphing is a third example. But I prefer the elimination method because I find it to be very fast. in order to use the elimination method, and let me go ahead and I'll write that up here. You know, what I prefer to use is, let's use elimination method, and I'll demonstrate what that is here in a moment. The elimination method for solving, you know, because it's saying use any method, so I'm saying let's use elimination method to solve this system. Well, if I'm going to use the elimination method, we need to convert and make sure that, you know, each of the two equations is written in standard form, so that the x and the y terms are both on the left side. And if that's the case, if we need to do that to support the elimination method, then this first equation, 9x equals negative 69 minus 7y, I'm going to go ahead and have to move, in the effect of moving, I'm going to eliminate the y term from the right side, and when we balance the equation out, it has the effect of looking like the y term moved. So we end up getting the first equation to look like this. I'll take it back to blue just for now. 9x plus 7y equals negative 69. So there's equation 1, but written in standard form. Standard form is ax plus by equals c. Standard form of a linear equation in two variables. Now we can bring over equation 2, because that's always been written in standard form, except that a is a negative number. We can forgive that because we're really just operating on solving the system and kind of foregoing the formality that a should be positive. You know, for true standard form, a should be a positive number. We would multiply this by -1 to make -4 a +4. But it doesn't really affect us. Here's the elimination method, though. I want to eliminate either both of the x terms or both of the y terms by turning one of them to the opposite of the other in the other equation. So what we're going to do is we're going to use either both x term coefficients or both y term coefficients, and I want to make these, I'm going to target y because the 7 and 4 are a little smaller than 9 and 4. 9 is a bigger number than 7. If we were to multiply these equations by numbers that we're going to kind of work out to turn the y's into their opposites, we could either do this with y or with x. I'm targeting the y's because 7 and 4 are smaller than 9 and 4. So they're just smaller numbers. I want to turn the y terms to their opposites. I'm going to multiply the top equation by -4 and the bottom equation by 7. And this is going to turn the y terms to their opposites. Look, -4 times +7 makes -28. +7 times +4 makes +28. -28y plus 28y. Those are going to add together to make 0. That's the elimination part of the elimination method. We're going to eliminate the y terms by using these multiples. So let's see all the way what happens here. These are going to transform now into resulting equations. So we're going to multiply both sides, every term, by these numbers on the outside, these red numbers. Okay, let's take it equation at a time. Negative times positive, negative times +9 makes -36x. Negative times +7 makes -28y, like we had planned. Equals negative times negative makes positive. I'm just going to go to my calculator and make sure I use the speed of the calculator. If I'm in an exam, definitely want to use the calculator. 69 times 4 to save time. 69 times 4 is 276, and that would become a +276. Okay, now let's do 7. Positive times negative is negative. 7 times 4 is 28, x. Now we're going to distribute to the middle term. Positive times positive is positive. 7 times 4 is 28, y. See, these are opposites of each other now. Equals 7 times 12. 12 times 7 in my calculator is 84, and it's positive times negative makes negative 84. Now here's the beauty of what we're shooting for. If we were to add these equations together, look, the reason we put them in, made sure they were both in standard form, is because it lines us up. It lines up like terms. X to the first plus x to the first remains x to the first. Negative 36, I'm going to go negative 36 in my calculator, minus 28, minus 28 equals negative 64. So this becomes negative 64x. Now, what was the special thing about that? The reason you chose these numbers was so that negative 28y plus 28y becomes 0. Look, there's the elimination method at work. We've eliminated. We just eliminated the y terms. We've eliminated y, the whole variable, from the resulting equation. Okay, equals, I have 276 plus a negative 84. I'm just going to go minus 84 in my calculator. 276 minus 84 equals 192. 192. Look, so here's the result so far. Negative 64x equals 192. Now to solve for x, we've eliminated y. To solve for x, we divide both sides by this number, this coefficient of x, negative 64, so that we get positive 1x. We want to know what 1x is worth. And balance the other side of the equation. So we get positive divided by negative makes negative. 192 divided by negative 64 is 3. So what we're seeing here is, when we say x equals negative 3, what exactly are we looking at? Well, if we go back up to what the interpretation of the solution is, what we've just found is x equals negative 3. We have found the x-coordinate of an intersection point. We found the x-coordinate of an xy ordered pair. Our job now is to find out what the corresponding y coordinate is of the intersection point. It looks like we actually do. These lines look like they do intersect if we were to think of it graphically. So now we can take x equals negative 3 and substitute negative 3 in for x into either one of these two equations. I personally, at this point, I want to substitute this. Substitute x equals negative 3 into the equation that has the smallest numbers. The equation between these two that has the smallest numbers is equation 2. So equation 2 looks like this. Negative 4x plus 4y equals negative 12. We're going to substitute negative 3 in for x. So when I read this and get ready for substitution in for x, negative 4x, I open empty parentheses, plus 4y equals negative 12. Here comes the substitution of our x equals negative 3 in for x. And at this point, what we would do is we would solve this for y. Solve for y. We would do that at first by simplifying. Negative times negative is positive. 4 times 3 is 12 plus 4y equals negative 12. Now we would subtract 12 from both sides so that we eliminate the 12, the constant from the left. Eliminate it. And balance the other side by also subtracting 12. So negative 12 minus 12, that's negative 24. Combine these terms. 0 plus anything is itself. So 0 plus 4y is 4y equals negative 24. And then we would divide both sides by 4. Dividing 4y by 4 gives us positive 1y equals negative divided by a positive 4 makes negative. 24 divided by 4 is 6. So here now, this implies that y equals negative 6. What would that be? Well, this should be the y-coordinate, negative 6. This should be the y-coordinate of the solution point. The point of intersection. If we make it all in color now, the same color, because we said our intersection point would be this red point. I'm going to look for an ordered pair in the solutions, in the answer choices that say negative 3, negative 6, and here it is. The ultimate way to check this and make 100% sure that these numbers work is we should substitute x equals negative 3 in equation 1 for x and equation 2 and simplify. And we should also take y equals negative 6 and substitute that into y and in both equations, simplify it and make sure that we get true. I'll leave that step up to you for checking.